find the area of the region common to the two regions bounded by the circle r equals negative 6 cosine theta, and the cardioid r equals 2 minus 2 cosine theta. So we really do have to take our time graphing this thing. Before I graph the cardioid, let's talk about the fact that this guy is a circle. That may not look like a circle to you. So let's talk about this guy. To get a really good idea of what this looks like, it would be easy enough to convert it to rectangular coordinates. Do you remember what the trick is? Since it involves r on the left side and a cosine theta on the right side. Multiply both sides by r. That's the trick. If you see r equals something times cosine, some constant times cosine, or r equals something, some constant times sine, that's the trick to use to convert if you want to convert to rectangular. And the reason I'm converting to rectangular is we'll recognize exactly how to graph it when we put it in standard form. So that you get r squared on the left side and negative 6r cosine theta on the right side. Convert it for me. What's r squared in rectangular coordinates? X squared plus y squared. And r cosine theta? So we have negative 6x, because r cosine theta is x. Then the idea is, okay, we put this in standard form. So how do we do that? What do we do with the negative 6x? Add it, and write it next to the x squared term. X squared plus 6x, leave a little bit of space, plus y squared. We have 0 left on the right side. And then we complete the square, right? To put it in standard form. Okay, what's half the coefficient of the x? So write down plus 3 ahead of time, and then what do you do with that? Square it. So you square it and add it on, balance things out. You better add it to the other side as well, right? So what does the standard equation turn out to be? Okay, x plus 3 squared is equal to, plus y squared is equal to 9. Okay, it's a circle. Center. C for center. What's the center? Negative 3, 0. What's the radius? 3. Now, could you get that from your calculator, plug it, leave it, staying in polar coordinates and plug it in the original equation? You bet. You bet. But it was an opportunity to review something, and I didn't want to pass it up. So, all right, let's graph the circle. Go up, down, left, right, 3 from the center of negative 3, 0. Doesn't have to be a perfect circle. Mine certainly is not going to be perfect. Point is, you want to graph, if you're finding an area, you better graph it, just like in rectangular coordinates. So there's your circle. Now for the cardioid. So how do we know it's a cardioid? Yeah, r equals 2 minus 2 cosine theta. All right, so a absolute value of a divided by b is, what's a? What's b? Yeah, take the absolute value, you do get 1, so it's a cardioid. Okay, so we graph this thing, just plot some points kind of like we just got done doing, r theta. Okay, now we're also going to want where the curves intersect, but I'll talk about that. Well, yeah, let's talk about it right now. So you'll see once I draw it why we need that point, but we're here, we're about to plot it, so let's plot that point right now. Oftentimes, when you want to find the region, the area of the region common to two curves, you're going to need to find the point of intersection, just like with rectangular coordinates. So let's go ahead and do that now before I graph it. So we have r equals negative 6 cosine theta. we have r equals 2 minus 2 cosine theta. How do we find the point of intersection? Set the right sides equal. So negative 6 cosine theta. So intersection point. What did I say it was? Negative 6 cosine theta equals 2 minus 2 cosine theta. So you set the right sides equal. And then you have to remember a little bit of your trig, how to solve simple trig equations, right? If you just have a trig function of the first power, you solve it like a linear equation. You isolate the trig function, don't you? That's what it breaks down to. So let's isolate the trig function. If we add 6 cosine theta to both sides, that leaves us with 4 of them, right? I'll put it on the left side, though. And then we subtract the 2 if we do it that way, so negative 2. So cosine of theta equals what? Negative 1/2. Okay, what's the reference angle? The reference angle is what you'd get if you stripped out the negative out of there. So the reference angle would be pi thirds. I like to call that alpha. And there's 2 quadrants between 0 and 2 pi. The 2 quadrants where the cosine is equal to a negative 1/2. Which quadrants? 2 and 3. So what are our 2 values for theta? We're going to have 2 intersection points. What are they? Yeah, so pi minus pi thirds would be 2 pi thirds. That would be the one in the second quadrant. And then the one we won't really need is 4 pi thirds in the third quadrant. Okay, do we know what r is? It'd be nice to know what r is, just for graphing purposes. So how could we get r if we know theta? Yeah, which one do you want to plug it into? Which one's the easier one? Probably that one, right? Negative 6 cosine theta. So r equals negative 6 cosine theta. Plug it in. And what do we get? Well, we know we get negative 1/2, right? So 3. Everybody buy that? So the extra point we're going to plot has theta 2 pi over 3 and r equals 3. That's the extra point we're going to throw in when we plot. And that'll be a point in the second quadrant. So it'd be in between pi over 2 and pi. So that's 2 pi over 3. Okay. So let's plot these points. Here we go. I'll do this one in red. So 0, 0. Pi over 3, we're out at 1. So at pi over 3, we're out a distance of 1. I'm just going to eyeball it. Pi over 3, 60 degrees, out a distance of 1, maybe something like that. Whoops. Something like that. And then at 2, we're at pi over 2. Or at pi over 2, we're at 2. So think of it as an angle. And then at pi, the straight angle, we're way out at 4, a distance of 4. 1, 2, 3, 4 in the direction of pi. And then that's the first, and then the intersection point I should have put in. 2 pi over 3, that has a reference angle of 60 degrees. So with regard to the negative x-axis, kind of heading at an angle of 60 degrees. And then you should intersect, let's see, 60 degrees, I don't know. Should look like it's about 3. That doesn't look too far off from 3. Now you have the top part of the graph, right? It's cosine, so it's symmetric to the horizontal axis. That means you'll have the bottom part of the graph as well. This point, you could just reflect down here. This point, same sort of deal. Okay, so when we draw it, we know it's a cardioid, so we draw it with that cusp. Kind of coming around like so. And then, let's see, this point would be reflected also to go through right there. Okay? Again, I'm taking an awful lot of time with this. I don't expect you guys to take this much time on the test. I don't expect your pictures to be pretty. They just need to be neat enough to be useful. Okay? Some of you are much better artists than me, and some of you will draw pictures that look much better than this. But this is useful enough. It's going to work. Now, can you tell me which area we're talking about? That's important to be able to identify that. So the area of the region common to the two regions bounded by the circle and the cardioid. So it would have to be in here, wouldn't it? Would you buy that? Okay, that's half the battle right there, you guys. Let me first draw just a radius through that. It's not part of the graph at all, but it'll help with clarification later. So let me just draw kind of a ray through it, or a line segment through it. So the R values that come before that angle have a different boundary than the ones that come after that angle. So the boundary on a representative radius before that angle, drawn from the origin to the first curve you hit, essentially, is going to be the curve in green. Kind of hard to draw because it's not a lot of space in here. But does everybody see that? That radius, if you draw a radius corresponding to an angle that's less than, it looks like it's got to be bigger than pi halves, but less than 2 pi over 3, you're going to hit the curve in green. You're going to hit the circle. Does everybody see that? But if you draw a representative radius after that angle, that corresponds to an angle that's bigger than 2 pi over 3, then the first curve you hit is the cardioid. So the thing is, if we want to find the area, we're going to have to break this up into two integrals. The integral that gives you, let me highlight it in blue. The integral that gives you this area has a different R. Long story short, the integral that gives you this area, does everybody see what I'm doing? It has a different R value than the integral that gives you, and we'll just look at the top part and double it, this area. Has a different R value. Do you guys buy that? So that means two integrals, and we'll split up according to the theta values. So what would be the integral that gives you the area of that solid blue region that I set up for you? Remember, the generic form is 1/2 integral some limit of integration to some limit of integration r squared d theta. We're going to have two of these. Some other integral 1/2, some other limits of integration, some other r d theta. So kind of as a template, let's start there. So for that solid area in blue, and I will zoom in on that again, what's gonna give me my limits of integration? Is it obvious what the top limit of integration is? It's 2 pi over 3. I think that's obvious. So let's go back here for this first integral for that solid region in blue. Hopefully it's obvious that the upper limit of integration will be 2 pi over 3. But where does it start? Yeah. You got to look at the curve in green, right? So here's where it's a little bit confusing. Well, maybe it's confusing everywhere. I don't know. But if you actually plot this circle in polar, we didn't actually do that, did we? But if you plot the circle in polar, it'll become clear, at least a few points, it'll become clear that no, you're not going to start at 0. And you could do this as easily on your calculator as you could by hand. But for the curve in green, remember the curve in green is -6 cosine theta. If you plug in 0, right, there essentially, what's the r value? -6. Oh, so if you start at the typical value of theta equals 0, you're actually you're way over here. So you see how far you'd be off by if you plugged in theta equals 0 for your bottom coordinate? Yeah, and okay, so and then what happens is the bottom part of the curve gets swept out. I'm running out of colors here. The bottom part of the curve gets swept out from 0 to, I think, pi over 2. Right? Because if you plug in pi over 2 for cosine, you'd be back to the 0, this point right here. And then you start carving out this part of the circle. So you have to start at pi over 2, long story short. Kind of crazy, huh? And I remember this being tough for me too, because it's totally different. You're not used to thinking radially and angularly, right? But it's just different. It's not necessarily hard. Keep that in mind. You practice it, it won't seem as bad. Use your calculator to help you with this. The appropriate r here is going to be what? What's the r? Yeah, that was the circle. So negative. So we'll clean that up in the next step. Okay, now the second integral is going to pick up where the first one left off, theta-wise, limits of integration-wise. So what's the lower limit on the second integral? 2 pi over 3. But now the closest boundary function is the cardioid. Okay. If we just, since there's so much symmetry going on here, if we just go from the 2 pi over 3 angle to what angle gives you this point right here in the cardioid? Pi. So if we just go from 2 pi over 3 to pi and double it, we'll be in good shape. So let's remember to double that right now. And then what's the r for that? Well, it's the cardioid, right? So it's 2 minus 2 cosine theta. And that's about as hard as your setups are going to get, thankfully. Let me clean it up, and then we'll answer your question, and then we'll take a break. So if I just distribute the 2, the 1/2s go away, right? So I'll just make it the integral pi halves to 2 pi thirds. Okay, it's -6 cosine theta squared. So how could I write that? 36 cosine squared theta. Everybody buy that? And then plus, let's see. The 1/2 is gone. Integral 2 pi thirds to pi halves. It's supposed to be pi. I don't know how I wrote pi halves there. So let's fix that. Okay, and then quantity 2 minus 2 cosine theta. And then what am I missing? A d theta on both of these? And then what am I missing here? Square it. And then I think I'm going to leave it there and let you guys take care of the rest of that. It's a standard evaluation for both of those integrals and the rest of it. Now, I do want to give you the answer. This would be great to practice over the break. These integrals, just make sure you're good at integrating, right? That's one thing we expect you to be good at by the time you get out of Calc 2. So this is good practice. When I don't go through the entire thing with you, it's good practice for you guys to come up with the answer. And so what is the answer? I have to find it here. All this junk is just 5 pi.